Okay, so we are now starting the last lecture of week 9 for Math 140 Business. I believe this is our 16th lecture, not 100%, but I think so. And today we are going to do a chapter on hypothesis testing, chapter 17, tests of significance. The basics. Tests of significance of the basics. So let's just recall quickly what happened last time. Last time we did confidence intervals. And the idea of a confidence interval is that we had no idea what a parameter was. So we take a sample and we get a value of our sample, and we form an interval around that value, and we say we're fairly confident that the true value is somewhere in there. That is the philosophy, that is the approach of confidence intervals. Tests of significance are completely different. For tests of significance, we have an idea going in of what a value is, but for whatever reason, we're questioning it. And we're going to form a test to see whether or not it's true. So for confidence intervals, we have an underlying belief of the value of some parameter, usually a mean or a proportion. That's step one. We have an underlying belief of the value of some parameter, and we decide to test to see whether that belief or an alternative is more likely to be true. Now, how exactly are we going to go about testing to see whether or not the original belief or a different one is true? How do we test a belief? Well, just like with confidence intervals, just like with everything in statistics, we take a sample. We take a sample and use the results of the sample to either reject or not reject the underlying belief. So what's an example of this? Suppose, anyone here eat at Subway?
Yes, I do.
Okay, you ever get a foot-long sub?
Yeah.
You ever wonder whether a foot-long sub was really a foot long or not?
Yeah. Wasn't it like 11 inches?
Yeah, there was the big thing in the news like about a year or two ago about this.
Yeah. Apparently though, like Subway, they ended up like it actually was, I think, a foot long.
You mean it somebody lied or what?
It was, well, I saw something that like the lawyers were just trying to make like a quick buck, but so Subway didn't have to end up paying anything at the end.
Gotcha. How nice is that? Go Subway. All right. Except for their whole Jared fiasco, they're pretty good. But anyways, so let's assume that Subway has been claiming for years now that their subs are 12 inches long. They're foot-long subs. And you go there a couple times and you're skeptical. You had a few subs. You kind of took out your ruler, which you carry with you because everyone does that, and you measured the sub, and you're like, oh, 11.3 inches, and the next one 11.6 inches, and the next one 11.4 inches, and you're like, you know what? I think Subway's lying to us. I think they're pulling a fast one. So let's test this. Let's test whether this underlying belief of a 12-inch long sub is correct versus the alternative that is actually less than 12 inches. So how do I do that? I take a sample of as many as I can because a small sample is always going to be a little suspect. And somehow I have to use the results of the sample to determine whether I'm going to reject Subway's claim or not reject it. In theory, does that make sense? The approach, the philosophy of what we're doing here?
Yes.
Okay. So the underlying belief is called the null hypothesis, denoted H sub 0, and always makes a claim about the true value of a parameter. Okay, so the null hypothesis H0 makes a claim about the true value of a parameter. For example, I might say the null hypothesis says that the true average of subway footlongs is 12 inches. I'm going to claim that the true mu, this unknown true value, is equal to 12. And in this case, my alternative hypothesis, HA or H1, is to say, no, the unknown mu is not 12, but rather the actual mu, the true unknown mu, is rather what? What is my claim in my subway example?
It's around 11.
Well, I don't go that far to say a specific value.
Okay.
I could do that. But it's just so much easier just to say, subway, you're lying. It's actually less than 12.
Oh, okay then.
Okay, so there are three so this is the alternative hypothesis. Alternative. Now, there are times when you make an alternative hypothesis that you specify a specific value. It's when we get to what's called the power of a test, we will talk about that. I don't think it's in this chapter, but there are times when we will do that. But for now, it's enough to say, subway, you're lying. I believe the true value is less than 12. So there are three types. There are three types of alternative hypotheses. There are three types of alternative hypotheses. A mu is less than some specific value. Mu is greater than some specific value. Or mu is what in relation to the null hypothesis claim that mu has a specific value. It's either less than that value, more than that value, and what is a third possible claim when I say the null hypothesis is wrong? I could say, no, you're lying, it's really less than. Or no, you're lying, it's really greater than. Or no, you're lying, it's really
equal.
Well, if it's equal, then you're not lying.
I don't. It's like smaller, bigger.
Well, what do you say?
More than.
Well, we have greater than already. We have more than. There are three ways you could be lying. Really, it's less than. Really, it's more than. Or really,
Doesn't exist at all.
no, that doesn't exist at all, but it's not equal to. I might not know whether it's more than or less than. I might just say, I don't think you're right. It's not equal to your value. And include the possibility of it being more than or less than as an alternative. So these are called one-sided because the results that would make me reject the hypothesis is only on one side. If I think it's really less than 12 and I get 15, I'm not going to reject the null hypothesis. In this case, I might suspect that it's 12, but I can't reject the null hypothesis in favor of the alternative. If you say it's really less than 12 and I do a test and I get 15 as my average, I'm not gonna say no, the null hypothesis is wrong in favor of the alternative. I might say the null hypothesis is wrong in favor of something else, but I can't reject it and say it's less than when I get a larger value. But for the two-sided one, whether you get smaller values or larger values, I might go ahead and reject the null hypothesis. So you guys all with me so far?
Yes.
Okay.
Yeah.
Now, if I believe, if Subway says that their Subway sandwiches are 12 inches long, and I take one sandwich and I measure it to be 11.9, am I going to claim Subway's lying?
No.
No.
No. What if I take 100 sandwiches and the average is 11.9? Would I say Subway's lying now?
No.
What about 1,000 sandwiches?
Maybe.
Okay, so there's some value at which a given distance away from 12 would make me reject the null hypothesis in favor of the alternative. What we have to see here is how the sample size decides what the cutoff is going to be. Because different sample sizes, I'm going to reject at different values, and we got to figure out what those are. So, very important. When doing tests of significance, which are what these are called, when doing tests of significance, we always work under the assumption that the null hypothesis H naught is true. So we're always going to work under the assumption that the null hypothesis is true. Now, if the null hypothesis claims that the true average, the true value is 12. So this is the null hypothesis right here, that the true value is 12. But I believe this is mu equals 12. But I believe that mu is less than 12. I'm still going to work under the assumption that the null hypothesis is 12. But where would I get results that would make me question the null hypothesis in this case? Where on my curve would I question the null hypothesis based upon the results of my sample? If I got this value, would I question the null hypothesis? Would I say, no, mu is really less than 12, Subway, you're lying? Where on my curve would the results have to be for me to say the left side? But the far left side. It can't be too close, because too close to 12, and I would say, okay, it's a sample. It's not going to be perfect.
That's within means of the.
Sorry?
But so, like, you want to make sure it's not within means of the actual value?
Yeah, if you're close to the 12, somebody will say, well, listen, you took a sample, okay? Yes, your sample average was slightly less than 12, but we still claim that if you took a whole population, it would be equal to 12. So we got to be far enough away from 12 that even Subway would say, yeah, okay, this is a result that doesn't make sense.
How many deviations would you go?
That's a great question. And that is what is called the level of significance of the test. So the level of significance of the test, the level of significance alpha of a test of significance, which is now why it's called that, is the probability of, well, take that word back, is the level of significance of a test of significance is the largest allowable probability of getting the results actually obtained or one even more extreme, and I will explain this in a minute, or one even more extreme if H naught is true. So in other words, suppose you get a result that had a 20% chance of occurring if the null hypothesis was correct. 20% chance. Would you say that you have convincing evidence that the null hypothesis is wrong if you got a result with a 20% chance of occurring?
Wait, Professor, sorry, what's the word before extreme?
More.
Oh, more extreme. Okay, thank you.
Or one even, the result actually obtained, or one even more extreme, if H naught is true. I think I had an extra word in there, but so the level of significance alpha of a test of significance is the largest allowable probability of getting the result actually obtained, or one even more extreme, if H naught is true. And what I mean by that is as follows. Suppose in general, you believe the null hypothesis is true, and under that assumption, you get a result with a 20% chance of occurring. Would you claim that you had convincing evidence the null hypothesis is wrong because you got a result that only had a 20% chance of occurring?
Wait,
Is 20%, is a 20% chance likelihood small enough that when it happens, you start to question the null hypothesis?
yes.
So let me ask you a question. If I had a,
Doesn't it depend on how many people, how
you
many?
know, let me try this again. Suppose I claim that I have a fair die, right? I give you a die to roll and I tell you it's fair. What's the chance of getting a 1 on that die if you roll it?
1 out of 6.
1 out of 6, which is what? That's like 16% chance, right?
Yeah.
Yes.
If it actually happens and you get a 1, would you be like so shocked and say, oh my God, this die is not fair? But getting a 1,
No.
I only had a 16% chance for it happening.
No.
No. You wouldn't question it.
No. Now let's say you got a 1 twice in a row. Would you start to question the null hypothesis now?
No.
What if you got a 1 100 times in a row?
Yes.
Okay, so somewhere between 2 times and 100 times, you dropped to a likelihood of occurring so small that you really had to question the null hypothesis, right?
Yeah.
Yes.
Okay, so I ask again. If you get a result that has a 20% chance of occurring under the assumption of the null hypothesis, 20% chance, would you question the null hypothesis? And just to compare it with a die, with a coin, with a die, it had a 16% chance, and you didn't question it then.
Also, no, you would have to have a lower probability of it happening.
So let's say you do something with a 10% chance of occurring, and it happens. Would you question the null hypothesis then?
No.
5% chance.
I don't think so.
1% chance.
Yes.
Okay. What about a 1 in a gazillion chance and it happens?
That's for sure you're questioning.
Okay, that's for sure you're questioning. Okay, so somewhere in between, we have a value where we say, okay, now, yeah, this couldn't have happened. So the answer is, not the answer, the choice that mathematicians or statisticians make for the cutoff is usually 5%. Usually, a 5% level of significance is chosen. And what this means is getting a result that has less than a 5% chance of occurring would be enough to make us reject the null hypothesis. Whereas if it had more than a 5% chance of occurring, it would not be enough to make us reject the null hypothesis. That is a choice statisticians normally make. Now, if the consequences of rejecting the null hypothesis when you shouldn't are great enough, you might choose a smaller number. You might say, okay, wait, no. I want 1% to be my level of significance. I want a really rare result to make me reject the null hypothesis. You might even say 0.1% or 0.100%. So Alberto, you asked, how many deviations is the cutoff? It's not so much the deviations as it is the percentage.
Okay.
Okay, we want to go far enough that the likelihood of getting this result, if the null hypothesis were true, is less than 5%. And a way of thinking about it is as follows. If the null hypothesis, where mu is equal to 12, is true, then our graph should look like this, right? It should be centered at 12. Suppose you got a sample average from your sample of 10.3. Suppose you got a sample of a sample average 12.3, and let's say from a sample of size 100, you got 10.3. And the question is, what's the likelihood that you got the result of 10.3 if the null hypothesis were really true? 10.3 would land somewhere out here. And the chance of getting 10.3 or something even more extreme than that is less than 5%. So what's more likely, that it's centered at 12 or that it's centered somewhere like this, nearer to 10.3?
Wait, what's the question?
Which is more likely?
Oh,
That the center of the distribution really is 12, like the null hypothesis claims, or
out of
or
all the
10.3?
Subway sandwiches
Yes.
in the world?
Yes, in the world.
Okay, 100 I don't think is enough.
Okay, how about 1,000?
No.
How about 10,000?
Yes.
Okay, so let's make it 10,000 just for the sake of the example. If my average of 10,000 was 10.3, you would feel justified in walking in the subway and saying, listen, I did a test of significance and I'm suing you because you're lying to the public. I believe, based upon my test of significance, that the true value is really much further to, or at least further to the left than what you claim. This is the idea of a test of significance. Under the assumption of being 12, the likelihood that I get my result is so small that I'm going to reject what you're saying in favor of an alternative hypothesis. In this case, I'm going to say it's less than 12. Therefore, you're lying to the public. I'm going to call the Better Business Bureau or whatever organization makes sure that businesses are honest to the public, and you're going down Subway. This is the idea. The question is, how do we actually perform the test of significance? And the answer is, it's actually easier than you think. Why? Because we're going to have the calculator do it for us. And we're going to see that the calculator actually requires very little information to do this. So let's do an example. You with me so far, by the way? Conceptually?
Yeah.
Okay, so we're doing an example right now. So let's take one from the book. I can take one anywhere. So let's do the following. Okay, so this is an example from the book. It says, does the order in which wine is presented make a difference? In one Canadian study, subjects were asked to taste 2 wine samples in sequence and indicate which was preferred. Both samples given were the same wine, although the subjects were expecting to taste 2 different samples. Like, you ever do a taste test and get the same one twice, and you're like, oh, the second one's better, when in reality they were both the same. So this is the situation. This is the experiment. So what are we interested in here? What's the null hypothesis? What are we thinking might happen? We are testing to see. Does the order in which wine is presented make a difference? That's the question. Does it make a difference? If it does not make a difference, then what percent of people do you think would choose the first wine?
Is it like the same kind of
Well,
wine?
yeah, it's the same wine. I give you the same wine twice.
Would
I
it
just-
be 50-50 just because
Can you repeat the question? I'm sorry.
You
Sorry.
think-
Sorry.
So I'm going to give, and in this case, I'm going to give it to 2,700, or is it here? It's where's the number? Yeah, n equals 5,400. So I'm going to test 5,400 people. And what I'm going to do is I'm going to give them wine and they're going to taste it. And then I'm going to give them a second wine and they're going to taste it. And I'm going to say, which wine do you like better, the first or the second?
Oh, I think most people are gonna say there's a difference in taste.
Even though it's the same wine.
Yes.
Okay.
Have you seen that thing where they like dye one of the wines red and they're both the same glass of like white wine? And then like most people said they like the white one better, even though they were the same wines. One was just dyed red.
Okay, so this is what we're testing. We're going to test what percent of people prefer the first wine. That's the question. Now, if it makes no difference, if everything was what was expected without any surprises, what percent of people would prefer the first wine, do you think?
%50.
50%. So the underlying hypothesis is that P, the true percentage of people who prefer the first wine, is 50%. And we're testing to see whether it's a difference. So what would the alternative hypothesis be if the null hypothesis was not correct in a situation where we're checking to see whether there's a difference?
it'd be two-way, right? You would want it to, you just want to know if it's not the same.
That's correct. This will be a two-sided hypothesis test where we're testing whether it's equal to 0.5 or is it not equal to 0.5. Null hypotheses always get an equal sign. That's first of all. The equality symbol always goes with null hypothesis. We said that earlier, or at least alluded to it, when I spoke about the three possible alternatives: less than, greater than, or not equal to. The equal sign always goes with the null hypothesis, but sometimes it takes a little thought to realize what the null hypothesis is. It's not always given. In this case, you have to ask yourself, if, like, what am I testing? I'm testing to see if there's a difference. So what will be the situation if there wasn't a difference? If there wasn't a difference, then people are picking randomly. And if people are picking randomly, it should be that half pick the first and half pick the second. That's what I'm going to see. I'm going to test that. Is it really that way? Or like Anahit says, is there a psychological thing where maybe people more like the second one as a general rule or the first? Let's see what happens. So I took a sample of 5,400. Now, in the example in the book, it says that of my sample, 2,790 preferred the first wine. Of my sample, 2,790 preferred the first wine. And the question is, based upon that result, what do I conclude? Do I conclude, go ahead.
Oh, I was just gonna say it's slightly over 50%.
So P, the true value is 0.50. P hat, which is my sample value, is 2,790 over 5,400. And if I go to my calculator and I just compute what that fraction is, it's equal to 51.6 bar percent. Now, let me ask you a question. even if the true value was 50%, would I really expect my sample to land exactly at 50%?
No.
No. So the question is not, is it 50% or not in my sample, but is my sample value close enough to 50% for me to reject or not reject the null hypothesis? Now, it's only 1.6% off, but it's a pretty large sample, which means the larger the sample is, the closer I expect to be to the true value by the law of large numbers. And therefore, maybe 1.6% is too far away. So what are we going to do? Let's take out our calculator. And where do you think we're going to go on the calculator?
Stats again?
Stats. And where on stats am I going to go?
Test.
Which test? It is test. Now the question is which test?
The sample test? One of the sample.
Well, there are 6 tests there. There's the z-test, the t-test, the 2 sample z-test, the 2 sample t-test, the 1 proportion z-test, and the 2 proportion z-test. So first, do we have 1 sample here or do we have 2 samples?
1 sample.
Only 1, right? We have 1 data. We're not comparing 2 different samples. We only have 1. So that eliminates 3 and 4 and 6. So it's either a z-test, a t-test, or a 1 prop z-test. And the answer for this case is, because we're dealing with a proportion, we're going to use number 5, the 1 proportion z-test. So when you do it in your calculator, the 1 proportion z-test, it should look like this. And we have 4 things that we need to input. The first one is P0. What do you think that is?
0.50.
0.50. The P0 is what the null hypothesis claims the true proportion is. In this case, it's 0.5. What do you think X is?
The number of people you tested?
Well, that's N. That's the sample size,
okay,
5,400.
That'd be the population.
Well, we don't have the population.
It would be 2,790.
2,790. It's the number of successes, the number of outcomes that are for whatever it is that you're looking for. In this case, 2,790. And which of the 3 tests are we going to use? The not equal to, less than, or greater than?
Not equal to?
Not equal to. And then we're going to hit calculate. And tell me what we see there that we didn't already know.
You have a z.
We have a z. What is z?
2.45.
Okay, about 2.45. And what else do we have?
We have a p.
We have a p, which is about what?
0.14.
Okay, and now we have to interpret these. We don't actually need both. We only need p, but it's a good understanding as to what z is and its connection to these problems. So z is your z-score. Okay, z is your z-score. We know that if you look at a standard normal curve where the mean is 0 and the standard deviation is 1, 2.45 means that you land 2.5 deviations to the right of the mean. So your data point is right here. Now, if you were to get what you got or something, or something even more extreme, ooh, oh, cool. Then that means you would have landed there because all of those points are more extreme than the one that you actually got, correct? More extreme meaning further away from the expected number. Yes?
Yes.
Yeah.
But also we have to include this side because it's two-sided. More extreme just means further from the center than 2.45. And I could have been further from 2.45 even had I been past negative 2.45, because it is a two-sided test. Now, what is the probability of landing in that more extreme region? Spoiler alert, they gave it to me.
1.4%.
1.4%. The probability of landing in what is called the critical region is 1.4%. What this means is, and this is called, by the way, the p-value of the experiment. P is the p-value. What this means is that if the null hypothesis is really correct, there's a 1.4% chance of getting the result that I got. What is my conclusion, therefore, based upon what we said earlier?
That the null thing is incorrect.
Well, we don't say it's incorrect, but we do say I'm going to reject the null hypothesis.
Reject it.
Because remember, in statistics, you can't ever confirm one way or the other unless you have the entire population. The best you can say is, this is what the data supports. Okay, the data supports rejecting the null hypothesis in favor of the alternative. And what is the alternative? In this case, in this example, what is the alternative?
That it's not equal to
That-
50%.
That it's not equal to 50%. And as such, people will psychologically, for whatever reason, prefer either the first wine or the second wine more than the other. Notice that we don't claim which way it was, but the data certainly supports one versus the other. In fact, what does the data support? That people like the first wine better or the second wine better?
The first wine better.
First wine better because it's more than 50%, our true value. But we weren't technically testing that. We were testing whether there's a difference. So we can only conclude that the data suggests that there is a difference. Whether that difference suggests that it's truly more or truly less, you have to go further and do either reevaluate this test or do a new test. But this one, the best I can conclude is that the data does not support 50% for each wine.
Wait, but
Yes,
1.4 is like smaller than 5%. So
that's
why?
right. So remember, this is the, what I write here.
So it has to be exactly 5%?
No, anything less than alpha, anything less than the level of significance, I will reject the null hypothesis. So 5% is the maximum value. Anything less than 5% is a rare enough occurrence that I will question the validity of the null hypothesis.
And so if it's exactly at 5%, you don't question it?
I mean, mathematically, it's never going to be exactly 5%.
Okay.
But if it was, if the calculator gave me exactly 5%, I would certainly make a note to say, I should study this more because the data is on the border.
Okay.
Okay, but you're not going to have a question where it's exactly 5% because, I mean, it's not. I mean, even if we cut off a couple decimals, if you go all the way till 10 decimal places or whatever the calculator gives, it's never going to be exactly 5%.
But I'm kind of confused. Like, why, if it's so small of a percentage, why are we questioning the null hypothesis?
Because the null hypothesis claims that the true center is right over here.
Yeah.
And we got this value that so far, would it be more likely to be over here?
No.
No, you don't agree with that? If the null hypothesis is correct, where on this curve would I expect my value to land? Where's the most likely area on this curve if this curve is really correct? Near what value?
I guess like
0?
Well, 0, right? In the center, no? Isn't that where this it's the highest, the most likely part of the curve?
Yeah.
Well, wouldn't you agree then that values near 0 would make me feel reinforced about the null hypothesis, and values far from 0 would make me question it?
That's not the part that I'm like confused about. I'm confused about the 1.4%.
So the 1.4% is how likely it is to get the result that you actually got, or even more, if I add up not just the number you got, but all the numbers past it, and I add up all that likelihood, that adds up to 1.4%, which is a pretty small number in the grand scheme of things. Would you agree? A pretty unlikely occurrence, right?
Yeah, so like, isn't it more likely to just go around like in the 50% range?
Yeah, so that's the whole point. I got something so unlikely. Do I really believe the null hypothesis is correct?
Oh, okay. I get it now.
Right? Small p-values.
So it has to be greater than 5%?
Well, if I want to reject the null hypothesis, it has to be a small number, less than alpha, less than 5%. If I don't want to reject the null hypothesis, it has to be a large number, more than 5%.
Okay, that makes sense.
Now, of course, if the problem gives you a different level of significance, don't always use 5%. Use whatever the problem gives you. Okay, so small p-values make us question the null hypothesis because we get very unlikely results. Okay?
Thank you, yeah.
Any results that forces us to reject H naught is called statistically significant. A statistically significant result is one so far away from what we expect that we really have to question whether it would have happened by chance. If something has less than a 5% chance of occurring, but it actually happens, we can say, well, hey, rare things occur. Or we can say, yes, I know rare things occur, but isn't it more likely that our assumptions are just wrong? That's the idea. How rare is this for us to conclude that our underlying assumptions are wrong? The answer, in general, 5%. Okay, if the problem gives you a different one, which it very well may do, then use the one that they do. So let's do the following example. Are boys more likely? Are boys more likely? We hear that newborn babies are more likely to be boys than girls, presumably to compensate for higher mortality among boys in early life. Is this true? A random sample collected in 2005 found 13,173 boys among 25,468 firstborn children. Based upon this data, which, by the way, was an observational study, because what experiment can you actually do here? But among 25,468 firstborn children, we found that 13,173 of them were boys. The question is, can we conclude from this that boys are more likely? So what is the null hypothesis and what is the alternative hypothesis with this question?
You want like values?
I want numbers will play a role. But remember, when it comes to the hypotheses, nothing from the sample plays a role because the hypotheses are always about the population. What is true about the population? We use the sample to test but the hypotheses themselves never involve the sample. So what is the null and alternative hypotheses in this example?
I think the null would be 0.5.
What is 0.5?
The percentage that boys and girls, well, boys are as likely as to be born as girls.
So how do I label that 0.5? What is 0.5? I want a symbol for it.
Oh, it's P.
It's P. It's the true underlying percentage for this population.
And then the H1 would be P is greater than 0.5.
This is a one-sided greater than test. We're questioning whether boys are more likely. So is the percentage 0.5 where they're not and therefore it should be 50-50? Or are they more likely? Is P really greater than 0.5? So what do? We take a sample. And what do we evaluate in the sample? Well, we want P hats, which is our sample proportion. What is our sample proportion here?
13,173 divided by 25,468.
13,173 divided by 25,468, which gives me 51.7%, which is certainly more than 50%. The question is it more enough than 50% to make us question the null hypothesis? So what do?
Stat.
Stat.
Test.
Test.
Number 5.
Number 5.
And then plug in the values.
And then plug in the values.
Let me get there, sorry.
No problem. Oh, that's so cool. I just saw something about the calculator I never knew before. Amazing. Wow. It's so cool. I love discovering new things.
Do we put greater than P of O?
Yes, this is a greater than test.
For P, I got 1.89.
No, you didn't.
I got 0.999999.
Well, no, it should be greater than. You did a double-sided.
Oh, yeah, I did.
But you who said 1.89, read the whole number, please.
The whole number for
Oh,
A whole number.
it's 1.8853522327, and it has like an E to the -8.
And what does that mean, E minus 8?
0.0000188, or is that enough zeros? It's like
No.
8 zeros in front of it. Or no, 8 decimal places forward, right?
Yeah, that's 7 zeros.
Yeah.
So let me ask you a question. Did we get a result that is likely enough if the null hypothesis was correct? If the null hypothesis is correct, we got a result that is likely or unlikely?
Unlikely.
Unlikely. I mean,
Like
unlikely.
really unlikely.
Extremely unlikely,
Yeah.
right? So if you were to get a result like this, would you say, oh yeah, well, listen, anything can happen?
No,
I mean-
no.
No, you'd say, listen, yeah, I know anything can happen, but this is so unlikely. I gotta reject the null hypothesis. In fact, what's my Z in this example?
5.50.
5.5. I am 5.5 deviations from the mean. Is that a likely outcome or an unlikely outcome?
Unlikely.
Unlikely. Isn't it more likely that the whole distribution should actually be centered somewhere further to the right?
Yes.
And that's exactly the outcome. That's the result that we make.
Professor, my calculator is coming out with something different.
What does your calculator come out with?
It's coming out with 5.884 for the Z.
So do me a favor, go back, tell me which number on stat tests did you press?
I chose number 5.
One prop Z test. Okay, what do you put in for the first line?
I put 0.5.
Second line.
Put 13,173.
Third line,
25,408.
468.
Oh, it's okay. Okay, then that was my miss.
And you put greater than?
Yeah, the second one, right?
The third one.
Oh, it's the third one?
Greater than, not less than.
Oh, okay then. All right, now I got it.
Okay, everyone with me? Okay, now, how do I calculate Z and therefore the p-value by hand? It's always nice that the calculator can do it for you, but it would be nice to do it ourselves. And the answer is, well, we already know how. We know that Z equals data minus mean over standard deviation. Isn't that the way we always calculate our Z-scores? Isn't that the formula for calculating Z-scores, data minus mean?
Yes.
So all we got to do is figure out what these values are for these examples. Well, the mean is just going to be our p hat. I mean, our data is just going to be our p hat. That's what the data gave us, right? That's our value that we calculated. The mean is going to be what we expect p to be under the assumption of the null hypothesis. Well, what do we expect p to be under the assumption of the null hypothesis?
0.5.
In our examples, it was 0.5. Well, you can imagine in other examples, it might be a different value, correct?
Yes.
So the number that we pick here, we just label it P0, and that's just the specific P under the assumption of the null hypothesis. So it's going to be P hat minus P0. It's going to be our data, our actual value that we got, minus the expected value, which in our case has been P5, 0.5, and in general, it's going to be P sub 0. And then we're going to divide by the standard deviation, which I don't think we've seen, and we're certainly not going to derive, but it's P0, 1 minus P0 over N, over the sample size. In our case, 0.5 times 0.5 divided by 25,468. We take the square root of that. And then we do 13173 divided by 25468 and subtract 0.5. And then we divide by that. And when I do that, I get 5.5. So it does give me the correct value.
What values for p hat did you just put 51.7?
Yeah.
And then for p of 0.5?
0.5. And then
So
N. And
why
then
don't you do p of 0 as 50% too?
it is 0.5 is 50%.
Okay, so my next question is, why'd you do p hat as 51.7, but
No, 51.7%, 5.517.
huh?
I didn't do 51.7 for p hat. I did 0.517 for p hat.
Okay, so 0.5.
0.517. Yeah, 51.7%, which is 0.517.
Just divide the whole thing by 100.
Why 100? Oh, yeah. Take the number and divide it by 100 is how to convert a percent to a decimal. That's correct. And if you do it, you get 5.5. From 5.5, how do I compute the p-value?
You need to take out like one of the charts.
Or I have a calculator do it for me.
Okay.
I mean, where's 5.5 on here? Well, that's 0. It's sorry, it's not 0.5, it's 0. Where's 5.5 on here?
To the right of 0.
Right, way out here, 5.5, and we want the likelihood of being past 5.5. How do I compute that?
Did you, oh, using the calculator?
That's how you do everything in statistics.
If you had the calculator, why didn't you just calculate the z-score with the calculator?
I did.
No, like, assuming you have a calculator.
Oh, well, why did I go about, what are you asking? Because when I did this on the calculator, it gave me both Z and P straight up. I'm just giving you how the calculator got it,
Oh, okay.
right? How do I calculate Z? That's the formula. That's what the calculator did behind the scenes.
Oh, okay.
And then how did the calculator get P? By doing exactly this that we're now doing. How do I calculate the likelihood of being in that little region over there? Anyone? How do I calculate being in that little region past 5.5?
What do you use the normal thing?
Yep, normal CDF, the way we always do it. What will be our lower? What will be our upper? What will be our mean? What will be our sigma?
Lower would be 5.5.
Lower is 5.5.
Upper is like 9s,
Upper,
unlimited.
Yeah, upper is a bunch of 9s, correct?
Mean is
0.
0, yeah.
Mean is 0.
Standard deviation is 5.5.
Standard deviation is not 5.5. Where do you get that one from?
Or the bottom number on the Z, which is I don't know what you got for that.
I didn't get anything. I just know it. What's our sigma for Z?
Would it be?
It's always been the same. Long before this chapter, we've always been the same.
It's 1, right?
1. Z is always a 0, 1 normal. Always. And what do we get as our result?
Wait, my bad. What did you put as the ST dev?
1. Z is always a 0, 1 curve, isn't it?
Oh, yeah. Okay. I got 1.9 times 8 times 10 to the negative 8.
Yeah.
Which is like close enough. Yeah.
I mean, it's within rounding the same as we got before. Agreed?
Yes.
Okay. So now a word of warning. Statistical significance. Let's make this black. Statistical significance is not the same as practical significance. For example, in the baby situation, 51.7% was a statistically significant result. It was far enough away from 50% based upon the sample size for us to reject the null hypothesis. But with that result, is anything going to change? Is life as we know it different? Do we do anything differently because of it? It's not a practically significant result. We're not going to design drugs to or do some kind of, I don't even know if you could alter chromosomes. I don't even know that kind of stuff. Can you do that? Can you genetically engineer gender?
I think you're able to do it with males now, but it's really expensive.
You can create males or change.
Yeah,
males.
I think you could choose the gender of the baby now, but it's really expensive, I believe.
Wow, that's crazy. That's nuts. But anyway,
I think so. I'm not.
right. But even if it's not around yet, I can imagine it will be around pretty soon. But the fact of the matter is, are we really going to do anything differently? Because we got 51.7% over 50%? Probably not. Okay, it's a statistically significant result. It's not really a practically significant result. So in general, I should write this in general, large samples can create significance. Large samples can create significance with small deviations. From the null hypothesis claim. You saw in our example of the babies, 1.7% was enough to create a statistically significant result. I mean, majorly statistically significant. I mean, the p-value was tiny. Small samples, on the other hand, will have a more difficult time generating significant results. Because with small samples, we understand you're going to have lots of variation. So you have to be really out there for us to claim the null hypothesis is wrong. Whereas for large samples, they're so tight around the true value that small deviations from the mean could create significance, and you might not have practical significance, even though you have regular, good old-fashioned statistical significance. Does that make sense? Are there any questions on what we've done so far today?
No.
Anyone? I want to, today is October 28th. No, so we're all caught up. We don't have to start chapter 18 today. And we are going to have the quiz, as I said, over the weekend. So yeah, unless there's any questions, that's 17. Any questions on 17?
Is there any like actual scenario where that little difference would make it be a practical use?
Say again?
Is there any situations where that small little variation might actually be a practical use?
I mean, listen, if I'm manufacturing some kind of device to be used in, computers, and they have to be a really more generating, and they have to be really precise to fit in to the millimeter, to the nanometer, then even small deviations can end up being significant.
Okay, so like medical tools as well, right?
Yeah, I mean, I'm sure you can conjure up many situations where you get that. No, it is. I said it was generating, didn't I?
I think you used the past tense, but yeah, you said generated.
Yeah, generating. Yeah. Yeah, but in general, questions like that are more practical in the sense of real life scenarios versus a statistics class where you're just kind of just doing the stats to determine whether or not you have statistical significance or not. Practical significance, that's more of a common sense question and a experience question than it is a statistics question.
Okay.
Does that make sense?
Yeah.
So are there any other questions?
No, sir.
Oh, sir. Okay. Well then, have a wonderful Halloween.